So we have a homework due tomorrow, right? That's homework 5. And then next week we have a prelim, our one and only prelim. Next Thursday, so a week from today, in the evening, 7:30 to 9:30. It'll be in 203 Phillips down the hall. I just sent out the formal announcement over Blackboard this morning, so all the information is there. The bottom line is, it's up through homework 5, up through the homework due tomorrow, and lecture-wise is up through the end of the previous lecture. So I'm going to just kind of recap the previous lecture to make sure we're on the same page, because that lecture had some issues. But none of the new stuff for today will be on the prelim. Yeah.
Isn't this 203 Phillips?
Oh, sorry.
You said down the hall.
Yeah, sorry. I don't know. I'm seriously getting old. Like, I didn't used to make these kinds of mistakes, and like you hit 40 and suddenly yeah, we're in 203 right now. 219 is down the hall, right? So yeah. So it's just right here.
Okay.
It's just right here. Sorry. That where also that happened? Like someone pointed out there was like a problem with the ComCloud, and we had extended the due date. And I said, oh, okay, well, luckily we have lots of time to figure this out because we don't need it again until lab 4. And then afterwards it dawned on me, like that's why people are asking me about the ComCloud, because they're still trying to do lab 2, which has not been turned in. It took me like a day for that to even dawn on me. Okay, anyway, so yes, prelim next Thursday in the evening. It will be right here. The email describes the coverage. It's basically like not counting today's lecture or anything after. It's the previous lecture and before. Discussion tomorrow will be review. I've posted all the old prelims from all 4 of the previous offerings of this class, at least as I've taught it. Bear in mind, I do kind of change the coverage year to year. I try to make the class better each year. So I kind of change a little bit what I cover and how I cover and what order and stuff. So, these classes are not like lecture for lecture matches of each other. Also, some years we had 2 prelims, some years we had 1. So, the timing was kind of off. So anyway, it'll give you a sense of the format and stuff. But, bear in mind the coverage doesn't exactly match what we have, we're having next week. So anyway, I mentioned the practice prelims because that's a good topic for discussion tomorrow. I think Umair plans to work through some of those problems, but the hope is that it'd be more kind of driven by you. So come tomorrow with questions, stuff you want to review, discuss, prelim problems you'd like to go through, whatever. It's more of a review session than a typical discussion. I have several things to return. So I got homeworks 2 and 3 back from the grader, so those are here. Remind me at the end of class. Any lab 1 regrades are here. I think there were like 2 or 3 of those. And then just anything unclaimed from past handouts, that's here too. We will post solutions to homework 5. We'll do that early next week, so you'll have those. I went through and updated the lecture schedule, so that's more up to date. I posted more lecture notes, that's up to date. We will have nothing due next week. There's no homework, there's no lab due next week, just the prelim. There'll be no discussion next week either. So the day after the prelim, no discussion, just chill or get caught up in other classes or start your weekend early or whatever. I'll post lab 3 fairly soon. That'll be due probably the week after the prelim, most likely. We will cover everything you need to do lab 3 in today's lecture. Okay, so I don't think it'll take 2 weeks to do, but I'll hand it out now just so that you can work on it ahead of time if you like. That's the first of the design labs. Labs 1 and 2 are just purely like, analysis, get familiar with things. Lab 3 is the first design one, but does not involve the ComCloud system. Okay, our channel for lab 3 is just a simple .m file, just a MATLAB script that I'll publish, just to kind of help us get our feet wet with these design problems in a very kind of constrained, simplified communication scenario. That's all I have. Any questions? We good? Okay. So I don't really have anything new to say about the topic from last lecture. My original plan had been to just kind of plunge into the next topic. But I was reflecting on the lecture from last Tuesday, like a week ago from Tuesday, which was our last lecture, and For those who were here, okay, you'd know that that lecture was not really like up to my usual standard of clarity and accuracy, and it might not have been up to the standard that you expect either for clarity and accuracy. So anyway, I can't go back and redo the lecture without sending us back like a whole lecture. I thought I would just kind of like give you the punchline with the formulas written up ahead of time, so I can guarantee there's no factors of 3 or 2 or n that are off. Just make sure we're all kind of on the same page. So I'll just run through this kind of quickly. It's just a punchline from the last lecture, and then we'll move on to the next topic. Okay, so the topic we looked at last lecture was what I called the bit power allocation. So suppose you have a channel that's diagonal. So the channel matrix is diagonal. So there's no ISI then. It's like a diagonal means by definition there's no ISI. So we have a channel with no ISI. But the gains across these two samples are not necessarily the same. Okay, so suppose that's the channel. So y equals hx plus z. H is diagonal, but not scaled identity. Okay, and at first blush, this seems like a kind of an odd channel. Like how would this ever arise in practice? Like it's a linear time varying channel. Like that seems like kind of a strange object. Okay, so you have to just kind of trust me that this actually comes up a lot. In fact, we'll see later in this lecture how this sort of thing comes up in real life. But for now, just take it as a given. This is the channel. Okay, it's no ISI, but the coefficients are not the same down the diagonal. Okay, and you have a power constraint. And the question is, like, if you have like an overall error probability allowance or tolerance PE bar, then how many bits can you send over this channel, and how do you do it? Okay, so how many bits do I put on each of these samples using PAM? How much power do I put on each one? If I have an overall pooled power constraint, I can kind of decide how much power to put here versus here. And it's not really clear how to do this. Should you put more power on like the weaker coefficient to overcome its weakness? Or do you put more power on the stronger coefficient because that's where you get the most bang for your buck? Do you put more power if you have more bits, or more power if you have fewer bits? Or, you can kind of drive yourself crazy thinking through all the permutations of this. So we did some math to try to get a feel for it. Okay, so the question is, how many bits can you send, and how do you allocate bits and power among these two samples that you're controlling at the encoder, the x's? Okay, so to parameterize this, we let ki be the number of bits you send using PAM over xi, and let pi be the power used in the ith sample. Okay, and then the overall optimization problem you can write kind of compactly if you just use certain abbreviations here. So you want to maximize the total number of bits you're sending across the two samples over the number of bits you send in each sample and the power on each sample, subject to the power constraint, and that the error probability of your scheme, so PE represents the chance that any one bit out of the K0 plus K1 is decoded incorrectly. You want the probability of that to be no more than PE bar. Okay, so we went through kind of a lengthy derivation of this. We did not solve it exactly analytically. We came up with an approximate solution that actually gives you a pessimistic bound, like a lower bound on K0 plus K1. Okay, and it worked as follows. So we solved it in the two sample case first, the one I drew up on the board over there. Okay, what the math said to do was set the two powers to be equal. Okay, even though the h's might not be equal, set the powers to be equal, but then send different numbers of bits over the two samples, depending on the strength, the relative strength of the two samples. Okay, so each sample gets the same amount of power, but it sends a different number of bits depending on how strong the gain is in that for that sample. Okay. So n is the noise variance, p is the overall power, these h's are the channel gains, PE bar is the error probability, tolerance, and so on. Okay, so that was for 2. And I think first time I did this, I had an n here that was wrong. I removed that, and then right at the end we said there's supposed to be a 3 there. So this formula got kind of edited or amended a bunch of times in the lecture, but I just copied it out of my book, so my book notes. So this is what it's supposed to be. So that's for 2. In general, it's kind of a similar story. You said all the powers would be the same, and just apply the same formula. The only difference is you have 2n here instead of 4. Okay, so think of this 4 as being 2 times 2, and one of those 2 is the number of samples n. Okay. So in practice, you'd optimize this numerically is what you do. Okay, so in practice, if you really wanted to like optimize your performance, you would start with a solution like this, okay, and then simulate it, see what error probability you get, and then tweak it a bit, try adding a bit, subtracting a bit, as needed. But this gives you kind of a starting point around which you can optimize. The k's that are quoted here are not necessarily integers. Okay, so you got to round it one way or the other. If you round it down, you know, you're guaranteed to have a lower bound because of the pessimistic nature of this calculation. If you round it up, you know, there's no guarantee that you're going to meet the PE bar error probability constraint, but you can certainly try it. There's no guarantee this is even positive. Okay, it can happen. You plug all this in, you get a negative number here. Okay, in that case, the thing to do is just zero it out. And then for that particular channel, delete its power, set it to 0, and allocate that power uniformly among all the other samples and rerun the calculation. And just keep doing that, okay, until eventually you only have samples left that are actually getting positive numbers of bits. Okay, so that's the recap from last time. People good with this? I think the overall story got through. It's just some of the details got messed up because I wasn't really being very careful. Okay. So let's move on then and start talking about how to communicate when you have ISI. This is communication over channels with noise and ISI. Okay, so suppose our channel model is the following. It'll take the form y equals hx plus z. Z will be the usual thing, so nothing new there. We've solved this problem when h is diagonal, right? That's what all this was about. So when h is diagonal, we have a pretty good handle on how to design encoders and decoders for this problem. And I want to consider the case where h is arbitrary. H is just an arbitrary matrix. Okay, and actually the h's that tend to arise in practice are not really arbitrary, so this is maybe assuming more than, or this is maybe making kind of weaker assumptions than we really need to, but just going to bear with me for a bit. The prelim break is right here, by the way. And can you read that? Right there. Okay. All right, so if h is diagonal, we know what to do. If h is not diagonal, then you have ISI by definition, and the question is now how do you communicate? So, you know, let's think about this a little bit. So you could certainly, you know, try to encode like one bit in each sample of x, like do antipodal signaling in each sample of x. Okay, that worked really well when h was diagonal because like each sample of x, you know, contained one bit, and each bit was encoded in exactly one sample of x, and h didn't like mix any samples together when it's diagonal, right? So each sample in x maps to exactly one sample of y, and so you get this vector of y samples. Each one has exactly one bit coded in it. Okay, and these bits are all decoupled, so you can just decode all the bits separately across the samples, and you know, life is good. Okay, when h is not diagonal, the issue is it smears everything together, right? You can encode one bit in each sample of x, okay, but then you know, each sample of x influences multiple samples of y, and moreover, each sample of y is influenced by multiple samples of x. Okay, so when you go to decode, I mean, you can still, the encoder can still pretend life is good, just encode one bit in each sample. But then the decoder has this rather challenging problem of trying to disentangle, you know, all these bits. Okay, and of course there's noise there too, which is making things even worse. Okay. So how do we get around this? Okay, so over the years, people have conceived of like many different methods for how to deal with the ISI. Most of these are kind of like of historical interest only at this point, okay, because people have kind of coalesced around a best practice that you know, is different from a lot of the ideas I'm about to show you. I'll show you a few of these just so you can kind of get a flavor of what people have tried in the past, and I'll show you the best practice, which is what we'll use in our labs. So let's just enumerate, you know, different ideas that either one could think of just naturally looking at that problem, or I can tell you ideas people have tried in the past. So maybe I can open up to the floor. Like, any ideas for how you deal with ISI? You have an arbitrary H to deal with. Yeah.
I guess my first guess would be to diagonalize H.
Okay. That's a pretty good idea. It's a little bit too good of an idea, actually. You're kind of driving toward the best practice, actually, that this is the trouble with opening up to the floor, actually. It's like you get answers that end up leapfrogging over like 15 minutes of lecture. What's a less intelligent idea than that?
Ignore the non-diagonal.
Sorry?
Ignore anything that's not on the H.
Ignore.
So set H to be just, or basically just zero out anything non the diagonal.
But we don't get to control H. That's the trouble. Like, H is the channel. We get to design X, like encode the bits into X however we want, and we design the machine that takes Y and extracts the bits. But H is just like this fixed, immutable object to us. Yeah?
So you only send one bit.
Okay. Yeah, so send one bit. I mean, you could just, if it's really like literally an arbitrary H, you could just send one bit, over this entire block. In practice, H is not really arbitrary. It's got this toplet structure, right? So coming from a linear time invariant system. So you have an impulse response. So what you don't really need to send like one bit over this entire time horizon. You just send one bit like per impulse response time. Because you send one bit, let the channel finish ringing, then send another bit, let the channel finish ringing to that. Okay, and then you won't have any interaction among these bits because they're spaced out enough. What's the problem with that? I would consider a meaning, then send another bit. Okay, the trouble with that? Yeah, you low data rate, right? In particular, in the ComCloud system, if you do 44.1 kilohertz sampling rate, like roughly what data rate would we get with that kind of approach? So if you do one bit per sample, you'd have 44.1 kilobits per second, right? But at 44.1 kilohertz, what's the duration of the impulse response, roughly? Anybody know? Top of their heads? Okay, I can just tell you, it's about 100 samples, more or less. Okay, so you incur a factor of 100 reduction in data rate if you try to do that, compared to we don't know we don't know you can send one bit per sample. Maybe that's just impossible. I can tell you can do that using the best practices. Okay, if you try to do this though, your data rate's gonna be like 1/100th of what you might otherwise get. Okay, so that's if you have an application where your data rate that you need is really low and you're looking for something simple, then by all means that will work. But our goal in this class is to try to push the performance. So this is not good enough for us. What else can we do? Any thoughts? Sorry? All right. I mean, at the decoder you can post-process. You can do all kinds of fancy post-processing, right? What's one fancy post-processing thing I could do with the decoder that would eliminate the ISI? I can multiply by whatever matrix I want of the decoder, right? I can take y and multiply it by anything. What might I multiply it by? Sorry? H inverse, right? Multiply by H inverse at the decoder. So maybe you would define a post-processed y, call it y prime, to be H inverse y. And y prime is just x plus noise, right? Call this z prime. Problem solved, right? ISI is gone. It's only 1:45. We can go home, right? No more. I mean, that's the whole point of this discussion is what to do with ISI. I just eliminated the ISI. Why is this not a satisfactory solution to the problem? And be more precise. So I claim we've solved the problem where H is diagonal. In particular, we've solved the case where H is identity. Now I've taken an arbitrary H and I've reduced it to one where the H is identity. So isn't this just the problem we just solved like over the last couple lectures? Can I just at this point just invoke the solution we had right here? No? Why not? Yeah. So when we did the case with noise but no ISI, our noise was IID Gaussian across the components, right? Y equals hx plus z, where z is IID Gaussian across the components. Okay. I just went all the way through by H inverse here. I eliminated the ISI. That's nice. Okay. What's the distribution of z though? It's not IID Gaussian anymore. It doesn't have a diagonal covariance matrix anymore. Okay. It's a covariance matrix will in fact be n, the scalar n times H inverse transpose, right? Okay, so I'd argue this actually has solved nothing. Okay, this hasn't really changed the problem in any substantial way. All it did was move the complexity around, okay? Because yes, I mean, you can consider this problem, certainly. This is a detection problem. You have 1 bit per sample, that's nice. But because the noise is not IID Gaussian anymore, the map detector is not the minimum distance detector anymore. In fact, the decision regions are going to be very complicated regions based on the shape of the, the covariance structure of Z. Okay, so you've not really made any progress on the problem. All you've done is kind of hidden the complexity in a place that's kind of hard to see it. Okay, but this is really just going around in circles. This is not really addressing the problem. Okay, let me show you a variation on this that is similarly plagued by problems that are maybe difficult to see at first. So suppose we just multiply by H inverse at the encoder. So pre-process. Okay, so encode the bits in X prime, 1 bit per sample. And then rather than sending X prime, send X, which is X prime multiplied by H inverse, like that. So take the vector we've encoded the bits, before you send it, multiply by the channel inverse, and then send that. What does the decoder see? Right? ISI is gone. Noise is untouched. Right? Pretty nice. Yet I claim this is also not a satisfactory solution to the problem. I'm not happy with this. You see the problem with this? For this part, I think it's helpful to think kind of physically rather than mathematically. So, I mean, mathematically it's kind of hard to see why this would really be a problem. But just think about intuitively what this means. So you're going to kind of take the signal you want to send, and you're going to alter it in a way that sort of cancels the ISI as it goes through the channel. What would be the cost of doing that? Is there a cost to doing that? It's helpful to think of ISI as like inertia, I think. ISI is basically the inertia of the channel, right? So a channel with no ISI has like no inertia. It just kind of responds instantaneously to each input as it comes in. Okay, a channel with ISI has inertia to it. As each sample comes in, it's still reacting to the previous samples. Okay? So we'd like a channel that has no inertia to it. I'm saying if you have a signal you want to send through a channel that's inertia free, you can sort of alter the signal itself so that as it goes through, it sort of like counters the inertia of the signal as part of its encoding. No? Sorry?
So you don't move at all?
No, you do move. I mean, ultimately, what you receive is going to be this. I mean, not moving would be like sending 0 to me. It's just encode x to be 0, and then you're not moving the system at all. Yeah.
You're encoding X in a way that doesn't account for your own inertia through the channel. It's based on everything.
No, actually, it does actually. It's because I mean, you're not really the noise is not really impacted by the channel, so you could actually kind of ignore the noise for this part. So, I mean, the only inertia we have to overcome is the inertia that's kind of due to our own signaling scheme. So there aren't really like exogenous inputs we have to worry about here.
Do you have to know X fully?
You have to know x fully.
So
But
you
let's-
just stream, you have to packetize it, right?
That's true. Let's assume we know x fully. I claim even then this is not the panacea that it might first appear to be. So think about it. Let's think about it this way maybe. So first sample of x. Think about how you construct from x prime here. Not mathematically, but just think about it more like in terms of an LTI systems approach. So first sample of x, let's just say, is the first sample of x prime. Okay, so that goes into the channel. Okay, next sample of x. If I choose it to be exactly equal to the next sample of x prime, that's not going to work, right? Because the channel is still reacting to the first sample from x. Okay, so what I send in for the next sample of x needs to be the next sample of x prime, with another term added to it that cancels the ringing that's still happening as a result of the first sample, right? And every sample is going to have to be encoded that way, right? Every sample is going to have the thing I actually want to send in, plus another term that cancels the effect of everything that came before. What's the cost of doing that? There's a cost to doing that. That's not free. See what I'm getting at? I'm using power, exactly. That uses power to do that. I have a power budget, right? I have a power constraint. Maybe I should have written it again. It would have maybe been more suggestive if I said we still have the power constraint here. Power constraint P on X. Like that. Okay, so all these extra terms I add to X prime in order to cancel the inertia of the channel, all that's using power. And it's not really sending fresh information. It's all wasted power just to sort of undo the ISI. Yeah?
Couldn't it be like negative? Like some samples you would actually have to send less power.
That's true, yes. So it could be that the signal that I want to send in a given sample and the term I have to add in order to cancel the previous ringing are actually like opposite signs. And so they kind of actually cancel each other, and I send less power than I would have if I wasn't trying to cancel the ringing. That can happen. On average, though, it's going to work against me. So it's exactly analogous to the fact that, like, if x and y are independent random variables, variance of x plus y is variance of x plus variance of y, right? The variance of the sum is bigger than the individual variances. You could say, well, can it happen that like x is positive and y is negative? They're independent. Can it happen that x is positive and y is negative, and so you add them and like the magnitude is smaller than? It's like, yes, that can happen, but when they're sort of incoherent, on average, it's going to hurt you. And that's what happens here too. It's like the bits you're sending and then the ringing that you're canceling are just sort of incoherent. And so yes, sometimes they'll cancel each other, sometimes they'll reinforce each other, but on average, you're going to pay a power penalty for it. Yes. Okay. So that's the issue with that approach. What else can we do? You just decode each bit separately, treating the others as noise. Treating others as Gaussian noise, i.e. just take like the ith bit and just try to detect whether that is 1 or 0 by doing a minimum distance test for that one bit, just kind of treating the actual noise plus the effect of all the other bits as just Gaussian noise. Okay. This actually works reasonably well in certain situations. So the issue is you take a really big, potentially a very large SNR hit when you do this, okay? Because you're not treating all of the other bits except for the one you're decoding as noise. Okay, so if you have a very low SNR system to begin with, where the power level is really low compared to n, okay, then just treating all the other bits as noise doesn't really hurt you that much because the noise is already, you know, kind of big. If you're in a high SNR system, however, this can perform very, very poorly. Okay, because in a high SNR system, you know, P is much bigger than R, so the noise is not really hurting you much. You might be tempted to put like a lot of bits in each sample, but then if you treat all the other samples as, you know, as noise, then all that power and all of those samples ends up hitting you as noise, and you take a big performance hit. Here's an idea that's kind of a variation on this one, the previous one, but a little bit more clever. So to decode the first bit, treating others as noise, then subtract its effect from the subsequent samples. And then repeat. Okay, so to decode the first bit, the first sample, okay, once you've decoded that, then you know what the first sample of x was, or the 0th sample of x. So you know what ringing is going to cause over the subsequent samples. You can subtract that from all the subsequent samples. Okay, then decode the next sample. Once you've decoded that, then you know what ringing it's going to cause for the later sample. Subtract that, and so on. Okay, sort of variation on the previous thing. Okay, so this is more intelligent than the previous one. You know, this also has issues you can probably spot. It's prone to propagating errors. Okay, if you decode one bit wrong, then you, in an attempt to cancel the subsequent ringing, you actually like potentially reinforce it. So you make it worse, and then you're more likely to decode the subsequent bits wrong, and then the whole thing can just sort of catastrophically, you know, snowball. Okay. Also, the first bit, when you decode this first bit, you're treating all the others as noise, right? So you know, you're likely to get that first bit wrong, and then cancel incorrectly, and you know, this is a very fragile scheme. Another approach is just decode x. Let's try to phrase this as, I'm going to say as one big map detection problem. You know, you can code one bit in each sample and you have n samples, right? So x has 2 to the n possibilities, right? Okay, so decoding x then, mathematically at least, you're trying to detect which of 2 to the n vectors you're observing when you observe that vector plus noise. So it's just a minimum distance test, right? And whenever you have like a finite set of possibilities for the signal is uniformly distributed over that finite set, and you observe the signal plus Gaussian noise, isotropic Gaussian noise, minimum distance is the map rule. So that's true here. Okay, so you know x, if I encode 1 bit per sample, you know I just have 2 to the n possibilities for x. I therefore have 2 to the n possibilities for h times x. Okay, so in principle, you know, you could just take y and just map it to the nearest of those 2 to the n possibilities for this vector, and that tells you what x is. Okay, you can see the issue with this though, right? If n is reasonably large, you have a huge number of possibilities here, and so you can't very well just compute the distance to each one. Okay, that's why we're looking for ways to break it up and do it bit by bit. Okay, etc. Okay, there's actually, you know, a huge library of schemes that people have come up with to contend with ISI. In my opinion, these are mostly of historical interest now, as I mentioned. Because nowadays, I'd say that the acknowledged best practice is to eliminate ISI using transforms. And don't even mess with all these kind of complicated time domain-based schemes. So transform-based approach. Okay, so I'm going to show you one transform-based approach first that I think is conceptually pretty clear. Like it's pretty clear why this is a good idea and why it fixes the ISI and so on. It's not very useful practically, however. It's conceptually very clear. Practically, it's not very implementable. But I'm going to cover it because it doesn't take very long. And I think it's useful to see it because it explains very clearly why transforms, are so powerful for treating ISI. We'll do that, and then I'll show you another approach using a different transform. It's a lot hairier, and it's very easy to kind of lose the forest for the trees. But it's a lot easier to make work in practice. Okay, so first approach is to use something called the singular value decomposition, or SVD. So SVD. Okay, the statement of which is if M is an M by N matrix. I'm going to write both the real and the complex version kind of at the same time. Okay, so if M is real, M by N, or respectively complex, M by N, okay, then M can be written as follows. M is U lambda V transpose. In a complex case, it's U lambda V Hermitian. Okay, where U is M by M orthogonal in the real case, unitary in the complex case. V is N by N orthogonal in the real case and unitary in the complex case. And lambda is diagonal. I'm going to put diagonal in quotes though because lambda is not necessarily square. So it's M by N diagonal. Okay, meaning lambda either looks like that. So it's, fat with a bunch of zeros to the right. Okay, or it's tall with a bunch of zeros on the bottom. Like that. Okay, and the lambdas are always non-negative. Even in the complex case, they're non-negative. And they're called the singular values of the matrix. Singular values of M. Okay? So we've seen some results like this before. Let's compare against some of the other diagonalization results we've seen. So if K is positive semi-definite, remember that? Then we know K can be written as U lambda U transpose, where lambda is diagonal and U is orthogonal. Right? What's another result we've shown where we've written a matrix with a a particular structure in diagonalized form? Where else have we seen that? We've done at least one other place. In our signals and systems discussion. So this was random vectors. This is where this came up. When we did signals and systems, we had a result. We said circular convolution turns to multiplication in the DFT domain. Right? What was our matrix way of expressing that? Do you remember? C is circulant. What can I say? It's diagonalized by the DFT matrix, right? Like that. Okay, where lambda in that case is square root of n times the DFT of the impulse response of that system. I would know this result for the prelim, and I would know this one too. SVD is not covered, right? It's after the prelim break, but these we covered long ago. Okay, so if you compare these, let's compare SVD against these results. So both of these results assume a particular structure, right? Assumes positive semi-definite, assumes circulant, okay? They also, however, assert something slightly stronger, right? So they both give you the same matrix on either side, just with a transpose over Hermitian. Look at the SVD, assumes no structure, okay? So weaker hypothesis, but a weaker conclusion too, right? And that you have potentially different change of basis matrices here, right? Okay. This is, I don't know, probably the most important result in linear algebra, I would say. I don't know what a competitor would be. It was an extremely powerful result, I must say. It's true for every matrix. Isn't this striking? Every matrix? And what else is true of every matrix? I mean, the set of matrices is like so vast and varied. You have all these, have permutation matrices and positive semi-definite matrices and orthogonal matrices and circular matrices. I mean, very little is just true for all matrices, right? Because there's so many different matrices with different characters. This is true for all matrices, right? Any matrix you can write like this. Okay, it's a remarkable assertion. I'm not going to try to prove it. Okay. We'll just use it. Okay, so let's go back to our channel. There's our channel. So you see where I'm going to go with this? Let's do SVD of H. Okay, that's the SVD. Okay, I can write Y is U lambda V transpose X plus Z. So far so good, right? Here's a matrix H, our channel matrix. SVD says any matrix can be written as yada, yada, yada. Okay, so we can do that in particular. This H, we know we can write that way. There's some orthogonal matrix U, some diagonal matrix M. In our case, M and M are the same. Our H is, we're going to assume it's square. Okay, so M and N are the same, so lambda is square. So we get to here. I've not changed anything, right? I still have the same channel. I just kind of decompose H that way. Okay, now what? what can I do? So when I multiply through by H inverse, you know, it eliminated all this, but it hurt the noise. I can multiply through by something else that will kind of partially annihilate this thing without hurting the noise, without changing the distribution of the noise at all, actually. What do I multiply by?
U transpose V.
Let's just try U transpose, actually. So let's consider a post-processed U, call it U1 maybe, which is U transpose Y. And I have Y1 is U transpose U lambda V transpose X plus U transpose Z. Right? So let me call this Z1, the transformed noise. Okay, that's going to eliminate the U's. I'm kind of halfway there. I can do something similar with V. What I'll do is I'll encode my bits into kind of a dummy variable x1, which only kind of exists within the memory of the encoder. Okay, and then instead of sending x1, I will send V times x1, which we'll call x. So then you have lambda V transpose V x1 plus Z1, right? So the V's cancel. And there we are, right? So one change of basis at the encoder, one change of basis at the decoder. Okay, and I've reduced the channel to one for which the channel matrix is diagonal, right? But not necessarily scaled identity, right? So the diagonal entries of lambda are not necessarily the same. They're the singular values of the original channel matrix, which could be different from each other. Okay, so that's why we went through all that stuff in the last lecture. How do you work with a channel where you have no ISI, but the gains on the different samples are different? That's why we did that, because of right here. Okay, so once we get to here, we have a channel where I have a diagonal matrix, but the diagonal entries are not equal. So all the bit power allocation procedure and stuff, you'd apply that here. Okay? Overall, this is quite clean. Like, it's one change of basis at the encoder, one change of basis at the decoder, the ISI is gone. Right? Pretty slick. Let's be careful though, okay? So the reason I don't like multiplying by H inverse at the decoder is because it changes the distribution of the noise. The reason I don't like multiplying by H inverse at the encoder is that it wastes power. So we want to make sure we're not falling into the same trap here. We want to make sure we're not just pushing the complexity into the noise or somehow kind of using up power needlessly when I switch from X to X1. Okay, so let's just check that neither of those is a problem. So distribution of Z1. Okay, well, Z is Gaussian. I'm applying a linear transformation to it. So Z1 is going to be a Gaussian vector. It'll be zero mean. What's the covariance matrix of Z1? Like when I have, here's my scrap sheet. So if you have matrix X, it's Gaussian with covariance matrix K. And then you consider AX. What's the covariance matrix of this? It's like one of the few formulas I recommended people memorize. A, K, A transpose. Exactly. Okay, so here, my K is just identity times N. That was the original noise. My A is going to be U transpose. So you have A, K, A transpose, right? U transpose U is identity. Okay, so when we multiply by U transpose, the noise realization changes, but its distribution does not. Okay, when you do this, sort of orthogonal change of basis to the noise, of course the realization would change, but the distribution does not. It's like entirely analogous to taking like a standard normal random variable and multiplying it by -1. Okay, that changes the realization, right? If it was positive before, it's negative now, and vice versa. But the distribution is the same as before, right? Because the Gaussian distribution is symmetric about 0. There's just like a vector version of that. Okay, the distribution does not change, although the realization does. But it's really only the distribution that we care about. So when I go to solve, if this is my channel now, I have no ISI and I have noise that is IID Gaussian, right? The covariance matrix of my noise is scaled identity, right? Okay, what about the power? Let's be careful about that too. Okay, so more precisely, we have a power constraint on x, on the thing you actually send over the channel. X1 is some dummy variable that exists in the in the mind of the encoder and the decoder. So the bits get encoded in here, but the power constraint is on x. So the encoder needs to kind of encode this in a way that when you transform it, you get an x that satisfies the power constraint. So the question is, what constraint on x1 does the power constraint on x imply? Okay, so consider the power in x1 on a realization basis, or the energy, I guess, since we're not dividing by n, the total energy in the signal. X1 is going to be V transpose times x. Like that, right? So x in terms of x1. Okay, so we'll get x transpose v, v transpose x. V transpose is identity. So the energy is the same. Okay, so when you go to encode bits in x1, you don't even really need to be aware that this transformation is happening. Okay, you can in a sense design the encoder and decoder for this channel right here. Just pretend this is your channel. Z1, Gaussian, covariance matrix identity times n. The power constraint the power in x1 needs to be at most p on average, right? Because the power in x1 is the same as the power in x, right? So when you go to design the encoder and decoder, you can just pretend this is your channel right here. Right, encode the bits in x1 to satisfy the power constraint, and then in the decoders decode them separately because they're not intermingling through the channel. All right, and the noise is IID, and this is exactly the channel that we solved in the prior lectures. Okay, so the overall system would look as follows. So the encoder would take bits. Encode bits onto samples using, say, PAM, and the bit power allocation procedure to help you decide how many bits to put on each sample and how much power to put on each sample. Okay, so there's a big block. Okay, what comes out of that is the signal we're calling x1. Okay, so x1 would have, each sample of x1 would have some number of bits encoded into it. Okay, x1 is not actually transmitted. We send x1 times v. So just multiply it by the v matrix, and that gives you x. So all of this is the encoder. Okay, this signal is what actually goes out into the channel. The channel will, of course, multiply by h. And it will add noise, z. So maybe I should make clear this is the channel here. Okay, and then in the decoder, first thing you do is do the U change of basis, or U transpose, I guess. Multiply by U transpose. All right, now you just have to code the bits along the samples. So decode bits on each sample. Separately from the other samples. And the bits come out. Okay, so the point is, like, you know, if you think of this as the encoder and this is the decoder, and you can almost just like view the V and the U as like part of the channel. I mean, think of this as the channel input and this is the channel output. So we call this Y here, I guess, and this Y1, right? So if you think of this as the encoder, sorry, this is the input to the channel, this is the output to the channel, then this is my channel right here. And we studied, you know, last week in prior lectures how to design a communication system for that. Okay, so once you understand that, okay, you know how to design these boxes, and then you just have to include the V and the U transpose multiplication, and then that's it. Okay. So I cover this as like our gateway transform, if you will. It kind of gets us hooked on the transform approach. I think it's conceptually, like, to me at least, it's conceptually pretty clear why, you know, using transforms is a good way of dealing with ISI. It sort of very cleanly reduces you to a channel with no ISI. So conceptually it's very useful. In practice, people don't tend to do it this way. For a couple of reasons that I think are not too hard to see if you think about this. So why, in practice, why do you suppose this is hard to implement? Mathematically, very clean. Mathematically, it's a great solution. In practice, no one really does it like this. Why not? Sorry? Yeah. How much time? Let's run some numbers. So, you know, lab 4, lab 5, your x and y vectors probably be like a couple seconds duration. So 44.1 kilohertz sampling rates. We're maybe talking like 100,000 samples, a couple 100,000 samples maybe. So n is like 200,000. Okay? So h is like 200,000 by 200,000. Right? We want to take the SVD of that. What's the complexity of SVD? Anybody know? It's what? Umair knows? It's n cubed. The complexity of computing the SVD is like n cubed. Okay, so n is like 200,000, and you know. Honestly, I mean, if the matrix is like 200,000 by 200,000, like good luck even storing it in memory in MATLAB, much less like actually running an SVD on this thing. And even, and you could argue, okay, the SVD you run once, you know, at like the beginning of the transmission, and then, you know, you don't need to, once you've computed, you know, V and U and lambda is used for the bit power allocation procedure here, you don't have to keep doing it. But even these matrix multiplications are quite expensive, right? This n squared complexity to do that matrix multiplication right there, right? This one too. So if n's like 200,000, you know, just storing these things in memory is going to be a problem, and certainly like trying to do this multiplication, you know, in any kind of real-time basis, you know, is not going to happen. Okay, so one limitation, just too much computation. If we're trying to do like gigabit Ethernet here, okay, and we need to do, every nanosecond we need to decode like, 1 bit, okay, then this is not going to work. It's too much computation. That's one problem. What's another? So I'll give you a tip for this one. We're still assuming a lot about the channel, right? We're assuming, no synchronization issues. We're assuming we know H exactly. How is this going to, how are we going to modify this to handle, say, the case where we don't know H exactly? So let me tell you, in practice, the way you learn H is you send a signal through, a known signal through, have the decoder measure it, and then feed it back. If the encoder needs the information, then you got to feed it back. There's no way for the encoder, like, unilaterally to learn H. Okay? It's got to send something through and then rely on the decoder to send back through some kind of feedback link. Okay? We have no feedback links in any of, in any of our math. The COM Cloud has no feedback link. There's no feedback in this class at all. Okay? In real life, there's often feedback. We completely ignore that in this class. Okay? So for our purposes, there's not a good way of feeding information from the decoder back to the encoder. So why is that an issue here? Sorry? Yeah, they both need knowledge, especially right here. So U and V are like very sensitive functions of H, right? When you tweak H a little bit, these U and V's are going to change potentially quite a bit. So you got to have a good estimate of the channel to know U and V, okay? And the only way for the encoder to know V is for the decoder to learn the matrix or learn V and then send it back. And that's a lot of information to send back, this whole V matrix. Okay, so I'll just say, this is hard to make work. When H is uncertain. And if H is changing, then you got to be constantly feeding back these V matrices to the encoder. Okay, so in practice, people don't do it quite that way. But if you're in a situation where you know H, okay, and either N is small, or N is like moderately large, but somehow you're doing this kind of all offline, you have a great deal of computation at your disposal, like this, this could potentially work. Okay, in particular, Lab 3, use that. Okay, so for Lab 3, the channel will be a MATLAB script that just takes we don't have the equation still up, it just takes the X that you give it and multiplies it by an H that you can just read right out of the file. Okay, there's no question about what H is, and it adds noise to it. Okay, and the N we have in mind is like 20 or something. Okay, so it's not super big. Okay, so for Lab 3, you just use this architecture right here. Okay, pull the H matrix out of the channel script I give you. Take the SVD of it. You're going to do one change of basis at the encoder, one change of basis at the decoder. That'll reduce the whole thing to this sort of channel where the lambda is given by the singular values of the H matrix. Okay, and just type, if you just type SVD in MATLAB, give it H, it'll spit all this out. Okay. So then this is your channel. Do the bit power allocation procedure to decide how many bits and how much power to put on each sample of X. Okay, or X1 as we're calling it here, and that's it. Yeah, that's Lab 3. Okay, so this approach will work for Lab 3. Okay, because I just tell you what H is. There's no uncertainty about it, and the whole thing is kind of small scale and is small. For Lab 4 and 5, this is not going to fly. Okay, Lab 4 and 5, we're dealing with the real world. N is big. H is not really known very accurately, so no good. All right. So next, I'll show you what to do in those situations. So any questions about the SVD-based approach first? Yeah.
So one more time, could you explain why the distribution of Z1 is the same as Z?
Yeah. So here's Z, right? Okay. And Z1 was defined to be U transpose, I guess, Z. that, right? Okay. So I'm going to use a theorem that we proved long ago, that if you have a random vector x, it's Gaussian with covariance matrix K, and A is invertible, okay, then AX is also Gaussian. The mean will still be 0. And the covariance matrix is A, K, A transpose. Okay, so this is something we showed back, it was like lecture 2 or something, lecture 3, just a fact about Gaussian vectors. Okay, so in this example, K is the scalar n times the identity matrix.
Yeah.
Good?
Starting to make more sense. Yeah.
Okay, all right. Let me just finish it just for completeness. A is U transpose. So A, K, A transpose is going to be U transpose n times identity times U. I mean, it's U transpose transpose. Maybe I should write it like that, right? So the transpose annihilate each other. A identity B is just A times B, right? So this identity is not doing anything. So you get N times U transpose U. So that's just N times identity. Okay? And like I said, the scalar version of this is like almost obvious. It's just saying that X and minus X have the same distribution if X is zero mean Gaussian. Okay, so just take this, generate a rand n in Gaussian and flip the sign, you still have a rand n. The realization is different from what you started with, but the distribution is the same. All right, other questions about the SVD? Okay, so this is the approach we'll use for Lab 3 to kind of get comfortable with just designing communication systems and the bit power allocation procedure and so on. But it's not going to scale for Lab 4 and Lab 5. So the issue with 1 here is that computing the SVD is too expensive. Okay, so we need an alternate transform that just runs a lot faster and ideally is not as sensitive to, where the change of bases you use to diagonalize is not quite so sensitive to H. Okay, so that's what we'd like. Okay, we can exploit the fact that H in practice is not just some arbitrary matrix. Like the SVD works for any matrix, right? Any matrix. So that's its power. It's also potentially its limitation. That's probably why it's so complicated to compute. Okay, because you're deriving all the structure out of an arbitrary matrix. In practice, our H is not arbitrary. Okay, it's toplets, and we can even make it to be circulant with a little bit of tweaking, right? So we're going to use that structure now. We'll assume H is circulant or toplets, as the case may be, and then see what we can do with that. So this is communicating over, we'll do circulant first, circulant channels, i.e. channels for which the H matrix is circulant. So suppose our channel is Y equals H, X plus Z. Z is the usual thing. And H for right now, we'll assume it's known, a known circulant matrix. Incidentally, there is one place where this is used in practice. It's not tended to use, people do not tend to use it to eliminate ISI over long time horizons. They do tend to use it when you have multiple antennas, actually. So in a wireless system, sometimes you have multiple antennas, the transmitter and the receiver, and you get like, cross coupling among these different channels. Like, it's not like antenna 1 at the transmitter only talks to antenna 1 at the receiver, and antenna 2 at the transmitter only talks to antenna 2 at the receiver, and vice versa, right? And in reality, antenna 1 talks to all of them, and antenna 2 talks to all of them, but the gains are all different. And it sure would be nice if you just had like independent channels across these antennas, right? And the SVD will do that for you. Okay, and that's a reasonable application of the SVD because it's very small. You know, your N is like 2 or whatever. It's the number of antennas. It's not like the time horizon anymore. So anyway, I'm hoping to talk about MIMO, multiple antenna wireless systems at the end of the semester. So if we get to it, SVD will come back up there. So it does have its uses, but people don't tend to use it for ISI. Okay, so let's suppose this is our channel now. If H is circulant, then it's diagonalized by the IDFT matrix, right? And lambda is now the DFT of the impulse response scaled by square root of n. Right? So, take your channel. I'm going to write H in this form. IDFT lambda DFT. See what I'm going to do? Same trick as before. I'm going to try to absorb these change of bases into the received signal and the transmitted signal, so that we're just left with the diagonal signal. And in the SVD case, that involved multiplying through, by some arbitrary change of basis matrix U. Here, just amounts to taking the DFT at the decoder. So just look at that, Y in the frequency domain. Okay, that is W transpose Y in the time domain. So that's W transpose W lambda, sorry, not transpose, Hermitian. W Hermitian W lambda W Hermitian X plus W Hermitian Z, right? I just multiply through by W Hermitian all the way through. W Hermitian W, that's IDFT DFT, right? Those cancel. W Hermitian Z, that's the DFT of the noise, right? This is literally the DFT of the noise vector. So just flip the arrow on the noise vector. We'll get lambda W Hermitian X plus the DFT of the noise, right? And likewise, W Hermitian X is just the DFT of the X, right? So basically, if you just switch to the frequency domain, that's what we're left with, right? ISI is gone, right? My channel matrix is diagonal. Okay, so, and actually there's a kind of a simple qualitative way of thinking about this. So if you have an LTI system, okay, it will tend to smear energy in time, unless its impulse response is a single impulse. Energy in one time domain sample, when you apply that to the system, to the filter, it will smear that energy over many samples, right? That's ISI. That's what we're fighting here, okay? That's in the time domain. An LTI system cannot smear energy in the frequency domain. It cannot move energy from one frequency to another, right? Let's think about it, right? The spectrum of the output is the spectrum of the input times the transfer function. So when you multiply by the transfer function, you can kind of attenuate or amplify in one frequency, but it cannot move energy. If the input had 0 energy in one frequency, the output has 0 energy in that frequency. LTI systems cannot create energy at frequencies where it was not there already, okay? So whenever that happens in real life, whenever energy sort of appears in a frequency where it wasn't before, it's either a nonlinearity or some kind of time variation, because LTI systems cannot do that, okay? So therefore, corollary of that, if smearing energy across samples is causing you a problem, then just switch to the frequency domain where that doesn't happen, assuming the system's LTI, all right? That's like one of the single most important ideas in this entire class, okay? So this is the basic idea behind lab 4 and 5. There are, you know, a lot of details to work through. My noise vector is now complex. My x vector, I'm now encoding bits in the frequency domain. That's complex. What is the power constraint doing here? Okay, how do I do map and ML when everything's complex? Okay, this opens up a whole can of worms once you switch to the frequency domain. So coming up next few lectures, we're going to work through all that. Okay, but like I said, don't lose the forest for the trees. Okay, at the end of the day, we're eliminating ISI by switching to the frequency domain like this. Okay, so I have office hours now if you want to chat about the homework or the prelim or whatever, and I'll see you Tuesday. Oh, and there are